welcome to the final video series for normal distributions. Not to say that we will be retiring normal curves for the entirety of the rest of the semester, but this is where we reach the end of a chapter. It also is where we reach the 1/3 of the way mark for this online content conversion. So pretty well done all around. Obviously, we can't rest on our laurels. We've got the majority of the online content left to discuss, but we are making good headway. And here is where we come full circle. Here is where we start to look at the answer to the question that got us into this normal discussion way at the start of the chapter. How do we approximate the binomial distribution curve? And I said, well, we'll just use the normal curve. But now it's time for us to assess how accurate the normal distribution actually measures a binomial distribution. So now we will finally answer the question, is it a good fit? Is the normal curve a good fit for a discrete binomial distribution? So a few things to remind you about. You know most of this already from when we were talking about binomial distributions. In order to have a proper binomial distribution, well, you have to have some number, a fixed number of distinct independent trials. Every trial has exactly two outcomes. We'll generally call them success or failure. They're mutually exclusive. And the probability of success stays constant across all trials. Of course, by extension, so too does the probability of failure. And just as a reminder, whenever you're doing this and you want to preserve randomness, make sure you're never sampling more than 5% of the total population. That's all stuff we've seen before. We all are familiar with those requirements. Now, for the normal approximation, there is one additional requirement, technically two, that we're going to throw on top of this. We're also going to have what we'll call a stability requirement. In order for the normal approximation to be stable, you want to make it so that you've got a big enough sample size so that if you take the probability of success and multiply that to your sample size, you got at least 5 here. Same for sample size times failure rate. Need at least 5 there. So you want to have a sufficiently large sample size. Otherwise, you're going to have wildly inaccurate models here. That's just something to hold on to. We'll see it come up a couple of times here in this next few videos. But if you have that, if you have stability, and if you have a proper binomial distribution, then what you're going to do is use those shortcuts that we talked about for binomial distributions. The mean is just NP, and the standard deviation is the square root of NPQ. Again, P and Q are probabilities in decimal form. And once you've got your mean, you've got your standard deviation. Well, look at that. You've got a normal curve now, right? You can start getting z-values, or z-scores, sorry. And the way you'll get z-scores is using continuity corrections. Basically, you're going to make it so that you use all the values that would round up or round down to the number of successes that you care about. And that's the whole process in a nutshell. So let me stop here with this example. What is the probability of getting exactly 2 heads in 8 coin flips? And in the next video, we will answer this in 3 different ways. We will do the proper binomial arithmetic for the binomial distribution. So if you want, you can dig out the formulas and try and do that yourself. We'll also use technology. And of course, we'll also do the approximation with the normal curve that we just talked about. So I will see you then.